Hello friends, welcome you all to the third lecture on function analysis and its application. In this lecture, we will discuss the distance between the subsets of metric space, diameter of the subset of metric space, bounded and unbounded metric spaces, and complete metric spaces. Following are the contents of the today's topic: distance between sets and diameters, bounded and unbounded metric spaces, complete metric spaces with examples. Before discussing the main topics, we will discuss the following theorems. Let X be a metric space and the points x, y, z be any 3 points in X, then dxy greater or equal to absolute value of dxz minus dzy. Proof: let X be metric space and points x, y, z be any 3 points of X, that is, this is the non-empty set X, points 3 points x, y and z lies in X, then dxy greater or equal to absolute value of dxz minus dzy. Proof: we have dxz less or equal to dxy plus dyz, because we know that third property of metric dxz less or equal to dxy plus dyz for all x, y, z belonging to X. That is, dxz minus dyz less or equal to dxy. That is this part, left side. dxz minus dyz less or equal to dxy. And again, dzy can be written as less or equal to dzx plus dxy. That is, dzy minus dzx less or equal to dxy. This part, left side. Okay. From 1 and 2, equation 1 and 2, we get modulus value of dxz minus dzy less or equal to dxy. That is, dxy greater or equal to modulus value of dxz minus dzy. Okay. Here dxz less or equal to, here in equation 1, dxy greater or equal to dxz minus dyz, and from equation 2 we have dxy greater or equal to dzy minus dzx, that is position reverse. So we can write dxy greater or equal to modulus value of dxz minus dzy. Hence proved. Next theorem: let X be metric space and let X, x dash, y dash belonging to X, these 4 points in X, then absolute value of dxy minus dx dash y dash less or equal to dxx dash plus dyy dash. Proof as above: dxy less or equal to dxx dash plus dx dash y. Suppose 3 points x, x dash, y are in X, then apply fourth property of matrix, that is dxy less or equal to dxx dash plus dx dash y. Again, we can apply the fourth property for dx dash y. We can write dx x dash, this is, and this one less or equal to dx dash y dash plus dy dash y. Okay. Thus, dxy minus dx dash y dash less or equal to dxx dash plus dyy dash. Okay. These terms we can write in left side, that is dxy minus dx dash y dash less or equal to dxx dash plus dyy dash. Again, we apply the fourth property of metric on the point x dash y dash, that is dx dash y dash less or equal to dx dash x plus dxy dash. Okay. Again, we apply the fourth property for dxy dash. So we can write this less or equal to dxy plus dyy dash. That is dx dash y dash minus dxy less or equal to dx dash x plus dyy dash. This terms can be written in left side dx dash y dash minus dxy less or equal to dx dash x plus dyy dash. Therefore, from 3 and 4 can be written as absolute value of dxy minus dx dash y dash less or equal to dxx dash plus dyy dash, because here dxy minus dx dash y dash less or equal to dxx dash plus dyy dash, and in equation 4 the position of left side reverse, dxx dash minus dxy less or equal to dx dash x plus dyy dash. Hence, we can write absolute value of dxy minus dx dash y dash less or equal to dxx dash plus dyy dash. Hence proved. Now, we can define distance between the subsets of metric space X. Let D be a metric on a set X. The distance between a point P belonging to X and a non-empty subset A of X is denoted and defined by dPA is equal to infimum of dpx such that x belonging to A. That is, let X be a non-empty set and A be subset of X. Any point P belonging to X, then the distance between the subset A and the point P defined by infimum of dpx such that x belonging to A. X is the element of A. Okay, that is the greatest lower bound of the distance from X to the points of A. This one. If P lies between A, then dPA is equal to 0. If P in subset A, then dpx is equal to 0. Second definition, distance between two non-empty subsets A and B of metric space X. It is defined and denoted by DAB is equal to infimum of dxy such that x belonging to A and y belonging to B. Suppose the metric space X and two subsets A and B. Suppose X belonging to A and Y belonging to B. Then the distance between the subsets A and B infimum of dxy, where small x belonging to A and y belonging to B. That is greatest lower bound of the distances from the points A to the points in B. The diameter, let XD be a metric space and a non-empty subset of X, then the diameter of A denoted by delta A or dA. It is defined by dA is equal to supremum of dxy belonging to A, that is least upper bound of the distances between points in A. Let X be a metric space and A be the subset of X, then suppose point in A, X, and another point Y. So supremum of dxy such that xy belonging to A. Supremum value is called the diameter of the subset A. For example, consider the usual metric D for R defined by dxy is equal to modulus value of x minus y. Let A is equal to semi open interval 1 2 and B is semi open interval 2 4. That is left side here open and right side closed. In this A, left side closed and right side open. Then diameter of A. What is the diameter of A? Diameter of A is 1 because here dxy defined the usual metric mod x minus y. So supremum value of dxy 2 minus 1, that is 1. And diameter of P, supremum as per definition of diameter, d is equal to supremum of dxy. So supremum of dxy of B is 4 minus 2, that is 2. And distance between the points 3 by 2 and subset B. Here points 3 by 2 in B, that is lies between the subsets B, okay, and B. So what is the definition of distance between the points P and subsets A is dPA is equal to infimum of this dPx, where x is the element of A. So here d 3 by 2 B is equal to 1 by 2 because points D P A is equal to infimum of D P x such that x belonging to A. So is equal to infimum value of 3 by 2 modulus value 3 by 2, okay, minus infimum value of this, that is 2, that is 1 by 2. So d 3 by 2 B is equal to 1 by 2 and d 9 by 4 B, that is this is a 9 by 4, that is 2 point something, and here 2.24, that is infimum of Px, okay. So 9 by 4 minus B, this is 2 4, 9 by 4, that is 2 point something, okay. Then 9 by 4 lies in B, that is d 9 by 4 B is equal to 0. This is not correct. d 5 B is equal to 1, okay. d 5 B is equal to 1. So this is infimum of mod 5 minus B, okay. So in Phenom value 5 minus 4 is equal to 1, that is D5B is equal to 1. Okay. Next definition, bounded and unbounded metric spaces. Let XD be a metric space. We say that X is bounded if there exists a positive number m such that dxy less or equal to m for every pair of points x and y of x. A metric space which is not bounded is said to be unbounded. Thus, a metric space X is bounded if its diameter is finite. Similarly, a subset A of X is said to be bounded if diameter delta A is finite. For example, let X is equal to a set of real number and dxy defined by modulus of x minus y, this metric space X is unbounded since diameter of R is infinite. The metric space X is bounded if its diameter is finite, otherwise unbounded. So, if X is equal to R, then the metric space X is unbounded metric space. Second, if a discrete metric space XD where D, XY defined by 0 and 1. If X is equal to Y, then dxy is equal to 0. If X not equal to Y, then dxy is equal to 1. Here, diameter is 1. Hence, discrete metric space is bounded metric. Complete metric space. Okay. First, we discuss the limits and convergent sequence. Limits of the sequence in XD and convergent sequence. Okay. What is the limit of sequence in XD? Let XD be a metric space and A and B sequence of X. We say that An approaches the limit L as n tend to infinity. If for every epsilon greater than 0, there exists a positive integer n0 such that DANL less than epsilon. Whenever n greater or equal to n0, then limit n tend to infinity An is equal to L or An tend to L as n tend to infinity. Okay, here it should be the non-empty set X, this one. Okay, and convergent sequence, if limit exists L in X, then we say that the convergent sequence. That is, if XD be a metric space and let An be sequence of points in X, we say that An approaches L, where L is in X as n tend to infinity. If given epsilon greater than 0, there exists a positive integer n0 such that DANL less than epsilon whenever n greater or equal to n0 depending on epsilon. We shall denote this by DANL tend to 0 as n tend to infinity. Another notation we can define as DANL tend to 0 as n tend to infinity or An tend to L as n tend to infinity. And we say that An converge to the point L in X. For example, let the sequence An is equal to 1 by n is convergent sequence converging to the point 0 in R with usual metric. Next, Cauchy sequence. Let XD be a metric space and An be sequence of points in X. Then we say that An is a Cauchy sequence in X if given epsilon greater than 0, there exists a positive integer n0 such that dan am less than epsilon for all mn greater or equal to n0. That is dan tend to 0 as mn tend to infinity. Theorem: a convergent sequence has a unique limit. And second, every convergent sequence is also a Cauchy sequence, but not conversely in general. Proof: first, if the limit of convergent sequence an is not unique, let it has two distinct limits a and b. That is, an tend to a and an tend to b, because we have two distinct limits a and b, so we can write an tend to a and an tend to b as n tend to infinity. That is, d an a tend to 0 and d an b tend to 0 as n tend to infinity by definition of convergent sequence. Okay. From the triangle inequality of metric, we can write DAB less or equal to DAN plus DANB. That is, DAB tend to 0 as n tend to infinity. Why? Because DANA tend to 0 and also DANB tend to 0. That is, DAB tend to 0. And we know that the property, if DAB is equal to 0, if and only if A is equal to B. So, by this property, we can define DAB equal to 0 if and only if A is equal to B. That is, limit converge uniquely at the point A. Okay, because A is equal to B. We show that the limit is unique. Second, every convergent sequence is also a Cauchy sequence, but not conversely in general. So, proof: let an be convergent sequence with the limit a, that is, an converges to the point a as n tend to infinity. Now, from the triangle inequality of metric, we can write DAM an less or equal to DAMA plus DAAN. Okay. This implies that DAMAN tend to 0 as MN tend to infinity, because DANA tend to 0. Okay, this tend to 0 and this tend to 0 as M and N tend to infinity. That is, DAMAN tend to 0. We show that AN is a Cauchy sequence as per definition of Cauchy sequence. The converse is not true in general, and it is shown by example of metric space which is not convergent Cauchy sequence. For example, let X be semi-closed interval 0 to 1 as a subspace of R with usual metric. Then sequence 1 by n is a Cauchy sequence in X but not convergent in X. For example, here 1 by n is a Cauchy sequence in X, that is, DAN AM is equal to absolute value of 1 upon n minus 1 upon m, because here define the metric as usual metric. Okay, and sequence 1 by n. Then an is equal to 1 by n and am is equal to 1 by m. So, DAN AM is equal to modulus of 1 upon n minus 1 upon m. Less or equal to, we can write this 1 upon n plus 1 upon m. Okay, as m and n tend to infinity, that is, this total term is tend to 0. Which shows that 1 by n is a Cauchy sequence in 0, 1. Here, this is the open at 0 side and 1 side closed. Tend to 0, which is not in x. Here, the 0, open interval 0 to 1, it means 0 not covered in this interval. So, and DAMN tend to 0 as MN tend to infinity, but 0 is the not member of this interval. Hence, sequence AN is not convergent sequence. Complete metric space. A metric space XD is called complete if every Cauchy sequence of points in X converges to a point in X. In the definition of complete metric space, we require that if dxn, xm tend to 0 as mn tend to infinity, then there exists x belonging to x such that dxn x tend to 0 as n tend to infinity. Okay. For example, any set with discrete metric form a complete metric space. Why? The function d such that x cross x to r be defined by dxy is equal to 0 and 1 if x is equal to y 0, if x not equal to y 1, then D is called trivial metric space on X or discrete metric on X. Let Xn be a Cauchy sequence in X, then dxm xn is equal to 0 if xm is equal to xn. Okay, and dxm xn is equal to 1 if xm not equal to xn. Now taking epsilon 1 upon 10 or 1 upon 100, in the definition of the Cauchy sequence, we define dxm xn less than very close value of 0. Okay, and hence we can write dxn xn is equal to 0. That is, xn converges to the point xn 0 as n tend to infinity. Thus, every Cauchy sequence converges to a point of x. So, x with discrete metric is complete. Next example, Rn is complete metric space with respect to the usual metric D defined by dxy equal to summation I is equal to 1 to n xi minus yi square whole power 1 by 2. Solution for x is equal to x1, x2 and so on xn, y is equal to y1, y2 and so on yn. Let us define dxy is equal to square root of x1 minus y1 square plus x2 minus y2 square plus and so on xn minus yn square. First, we have to prove D is metric space and then completeness. Okay. To prove the complete metric space, first we have to check the all condition of metric is defined or not. It is a metric space or not. Okay. So, already we have proved this example as a metric space in second lecture. So, in this lecture, we prove the completeness of Rn. Since Rn is a metric space which has been proved in lecture 2, hence we avoid here the proof of the metric. For completeness, let xm be a Cauchy sequence, that is xm is equal to xm1, xm2 and so on xmn. This is the notation of Cauchy sequence. Then for each epsilon greater than 0, there exists a positive integer n0 such that dxm xl less than epsilon as per definition of Cauchy sequence. That is square root of xm1 minus xl1 square plus xm2 minus xl2 square plus and so on xmn minus xln square less than epsilon, because here defined dxy is equal to this. So dxm xl can be written as square root of this. From this we have xm1 minus xl1 square plus xm2 minus xl2 square plus and so on plus xmn minus xln square less than epsilon square. Square of the equation 5 we have this one. Since sum of the n terms less than epsilon square, it means each term of this sum is also less than epsilon square. So we can write first term less than epsilon square, second term also less than epsilon square, and so on. That is taking square root of all terms. That is modulus of xm1 minus xl1 less than epsilon mod xm2 minus xl2 less than epsilon and so on xmn minus xln less than epsilon. This shows that xl1, xl2 and so on xln are Cauchy sequence of real numbers for L is equal to 1, 2 and so on n, because x is equal to x1, x2 and so on xn, that is x1, x2 and so on xn as individual in R. So here a Cauchy sequence xm defined as xm1, xm2 and so on xmn. It means as individual each point in R. So here each point xm1, xl1 less than epsilon, xm2 minus xl2 less than epsilon, and so on modulus of xmn minus xln less than epsilon. So this shows that xl1, xl2 and so on xln are Cauchy sequence of the real numbers for L is equal to 1, 2 and so on n. And we know that R is complete. It means each points converges to the points of R. Suppose xl1 converges to the point x1, xl2 converges to the point x2 and so on xln converges to the point xn as L tend to infinity in R with usual metric. Hence, we have xm1 minus x1 less than epsilon mod xm2 minus x2 less than epsilon and so on modulus of xmn minus xn less than epsilon for all m greater or equal to n0, because here xl1 converges to the point x1, xl2 converges to the point x2, xln converges to the point xn. That is this. Using the above step, this and from equation 5, we put the value xl1 as x1 and xl2 as x2 and so on xln as xn. Then we have this square root of xm1 minus x1 square plus xm2 minus x2 square plus xmn minus xn square less than epsilon. What is this? This is the dxm x less than epsilon for all m greater or equal to n0, where x is equal to x1, x2 and so on xn. Thus, every Cauchy sequence xm in Rn converges to the point of Rn. This is the convergent point. X, this is belonging to Rn. Hence, Rn with usual metric is complete metric space. Next example. The space L infinity is the set of all bounded sequences. X is equal to x1, x2 and so on xn. Y is equal to y1, y2 and so on yn and so on. Where mod xn less than infinity, mod yn less than infinity, because this is the bounded sequences of scalars with metric dxy equal to supremum mod xn minus yn, such that n belonging to n is complete metric space. Solution. L denotes the set of all bounded sequences. If x is equal to xn and y is equal to yn are any 2 points of L infinity, we define dxy is equal to supremum of mod xn minus yn, such that n belonging to n. Here D is metric on L infinity. Okay, so this is the proof of this is very simple. So we can prove and already discussed in lecture 2. So to prove of this space as metric can be avoided here. For completeness of L infinity, let x is equal to sequence xn, n is equal to 1 to infinity, which is a Cauchy sequence in L infinity, and each xn has xn1, xn2 and so on xni and so on. And as per definition, this is a bounded sequences, so xni less than infinity. Then for each epsilon greater than 0, there exists a positive integer n0 such that dx and xm equal to supremum xn I minus xm I for all mn greater or equal to n0 supremum I. Okay, as per definition. It follows that for each fixed I, xmi is a Cauchy sequence in R. Here I is fixed. Okay, I is equal to 1 to ... So here for all I, this one and individual xni minus xmi less than epsilon. Okay, as per definition of Cauchy sequence, dxn xm less than epsilon. Okay, that is supremum I xm I minus xn I less than epsilon. That is xm I minus xn I also less than epsilon for all I and fixed. So as xmi minus xni less than epsilon for fixed I, that is the xmi is a Cauchy sequence in R for fixed I. Since R is complete, each one of them converges to the some real numbers. Suppose xmi converges to the point xi. Okay, here xmi minus xni less than epsilon for all mn greater or equal to n0, that is this is a Cauchy sequence for fixed I. Hence a sequence xmi converges to the point xi. Okay, that is xmi converges to the point xi as m tend to infinity. Then for each fixed I and for n greater or equal to n0, we have mod xni minus xi less than epsilon. From above step and equation 6, we can write dxnx equal to supremum I mod xni minus xi for all n greater or equal to n0. Now we have to show that x is the element of L infinity and xn converges to x in L infinity. Since xni is convergent sequence for real numbers for each fixed I, so it is bounded. Hence, mod xi can be written as mod xi minus xni plus xni. Here we have added xni and subtracted xni, that is mod xi minus xni plus xni. This less or equal to mod xi minus xni plus mod xni. Okay. Since xni is a convergent sequence for real numbers for each fixed I, it is bounded. Hence, mod xni less or equal to k for all n. Since we can take epsilon less than m, we get from equation 7. Here, xni minus xi less than epsilon. Suppose this is less than m. M is a positive real number. So, here epsilon less than m and this portion from equation 7 less than epsilon, that is m plus xn I, this is also bounded by k. So, mod xi less or equal to m plus k both positive real number. So, mod xi less than infinity. This implies that xi belonging to L infinity. Further, supremum I mod xi minus xni less than epsilon. This implies that dxxn less than epsilon, because dxxn defined by supremum I xi minus xni, that is dxxn less than epsilon for all n greater or equal to n0. This shows that xn, this is not xni, it should be xn. xn converges to the point x in L infinity metric, and x also belonging to L infinity. Therefore, L infinity is a complete metric space. In this lecture, we have discussed the distance between the sets and diameter of the surface of metric space and bounded, unbounded metric spaces and complete metric spaces with examples. These are the references: function analysis by George Beckman and Lawrence Naresy, Dover Publications. Second, introductory function analysis with applications, John Valley, written by Erwin Krejcik. Third, function analysis, New Age International Publishers by B.V. Lemieux, and function analysis by Walter Rudin. Thank you for your attention.